To continue, now we have to Professor Mauro Rincón to introduce to Professor Wladimir Neves. You can start, Mauro.
Thank you, Juan. I will present the biography of the Neste speaker, Wladimir Augusto das Neves, em português. Ok? Bom, Wladimir Augusto das Neves, ele foi formado com dignidade acadêmica em Engenharia Mecânica pela UFRJ, ele é mestre em Engenharia Mecânica também pela UFRJ em 1990, doutor em Matemática pelo Instituto de Matemática em 2001, ele fez pós-doutorado na École Normale Supérieure de Lyon, na França, em 2003 e 2004, professor visitante na Oxford University, Inglaterra, 2011 a 2012. Atualmente é professor do Instituto de Matemática, professor titular do Instituto de Matemática, e está como diretor do Instituto de Matemática. Trabalha em EDP, equações de evoluções e mecânica do contínuo, lei de conservação. Ele é bolsista nível 1 do CNPq e bolsista de cientista do nosso estado. Ele tem orientações, ele tem 6 orientações de mestrado, 5 orientações de doutorado, 1 pós-doutorado e 1 de iniciação científica. O Wladimir tem 30 artigos publicados e eu não consegui o número de referências, de citações dele, mas a palestra que ele vai dar hoje para nós, o título é Nonlocal-fractional Theory and Application to PDEs. Paulo, Wladimir, thank you.
Okay, Mauro, thank you very much for this kind introduction. And I'd like to say thank you for Juan to invite me for this talk. He called me some days ago, on a Sunday morning. I was starting to open my computer and I received a call from Juan. Wladimir could give a talk? Yes, so it will be my pleasure. Okay, could tell you about these homogenization problems? Yeah, it's okay. So Juan, so sorry, I'm not going to talk about homogenization. I like so much homogenization problems as well. But I think the last talk I gave here was the homogenization problem, I think so. And I'd like to say more than that. I'd like to say that this seminar is a success seminar. So I congratulate all of the main guys who organized this seminar, in particular Juan, who is the Moscow man to invite the guys, something like this. So so I should say congratulations for the seminar. So I'm talking about Nonlocal-fractional theory, which is another subject I like so much. And then I make a propaganda, Nonlocal-fractional theory and application to PDEs. It will be exactly the same title of a section in these 200 years from Brazil, Portugal, that will be organized, which is organized from Sociedade Brasileira de Matemática e Sociedade Portuguesa de Matemática, that will be held in Salvador on 14 to 20 of August. Okay, so it will be a pleasure to receive all of you in this well meeting from the Matemática from Portugal and Brazil. I am going to talk about the motivation, or the outline of my talk. It will be the motivation, why non-local operators are important. I will give you a brief introduction. And then I will talk about 2 fractional evolution problems, so 2 scalar problems more related to bounded domains. Then I will talk about 2 systems of partial differential equation, 2 systems which are fractional partial differential equation. And I will make a joke here, 2, 2, 2, and more related also. I just mentioned the titles of this work. Most of these talks today, you'll be in joint work with my former students. My former student, Gerardo Aroto, which is now a professor in Alagoas, and my former student, Dionísio Orlando, which is professor in Lima. And also the related work will be now my other postdoc, Mauro, is Lauren Bonaldo, which is now a postdoc here at UFRJ. Okay? Okay, let's see what's not going on. So concerning this motivation, so I will talk about this anomalous diffusion. It's very important context where fraction of a class of pairs comes up is anomalous diffusion. This is a phenomenon which is extensively observed in some physical, chemistry, and biological fields and some problems, okay? And then to characterize anomalous diffusion, a phenomenon, you could use, for instance, a constant order fractional diffusion equations, and you could become some well-known tremendous success nowadays. More than 10 years that the first nice paper from Caffarelli Vasquez. For instance, the application of Levy process to describe the anomalous diffusion leads to partial differential equations involving fractional Laplacian. So this first motivation is anomalous diffusion idea, okay? Another type of motivation to study, to work with non-local or fractional Laplacians, for instance, is that give you a suitable regularity. What do I mean by a suitable regularity, okay? It's well known that any kind of real process modeled by continuum mechanics may have a dissipation. Also, they could have or even develop jumps in many applications, from more or less related to somehow to conservation laws and some exact type of problems. Since to have jumps is not allowed to have the Laplace operator in your model. On the other hand, the fractional Laplacian accept the existence of shocks, depend of the explained S, and also give an amount of dissipation. So somehow, partial differential equations driven by fractional Laplacian could give you enough regularity, which is very important to obtain a priori estimates and pass to the limit to have compactness, and is enough regularity of solution in a large class of real applications. This is the main point, okay? Okay, so what is, continue to be introduction now, what is the basic idea of fractional evolution model? Since we are going to talk evolution model, well, the simplest idea of a fractional evolution model is to replace Laplacian by fractional Laplacians. So therefore, one obtains the fractional linear heat equation. For instance, now if you don't care about I am not going to talk about the idea of constitutive relations that comes from fractional derivatives. If you are interested on that, it could see, for instance, the paper, the work from Miroslav Shilihav. It's very important, okay? But just to give you a naivety, if you want to consider initial boundary value problems, so I mean, if your domain is bounded, and since in particular they are more realistic ones from the real physical applications, this non-divergence form is not good to give a standard notion of weak solution. So if you replace just Laplacian for fractional Laplacian, somehow if you are in bounded domains for scalar equations, you are in trouble to integrate by parts, something like this. It's a simple idea. So continue the introduction, I talk about the fractional porous media type equation. So let us consider the following equation. So you have the derivative of time of rho plus the equation of rho v equals 0. So it's a continuity equation. And v is somehow minus gradient of p, and p is a function of rho, where rho is the density, okay, it could be think like density, v is the velocity field, and p is the pressure. So this nice and well paper from Luis Caffarelli, Luis Vasquez, in ARMA 2011, proposed the relation of the pressure P in non-local form. So P of rho is kappa rho, where kappa is the inverse of the fractional Laplacian. So this is why I said it's a fractional porous media equation. So this become a well-known paper. In fact, they consider, Caffarelli and Vasquez consider the equation dt of u equals divergence of u grad kappa of u. So somehow they give you a nice structured divergence form applying the idea of fractional Laplacian. Okay, in particular here, if you do not pick the first u, you have divergence of grad is Laplacian or minus Laplacian, it could be minus Laplacian, and k is minus Laplacian minus s. Okay, So, and the summary conditions, they could show existence of solution of the Cauchy problem. So they are considered the problem in our Rn, okay? So since the problem is in our Rn, so I'm going you have this definition of the Laplacian by the Fourier transform, which means that the fractional Laplacian is a pseudo-differential operator with the principal symbol modes of Cauchy a power to s from 0 to 1. It's well known nowadays. It's well known also that the fractional Laplacian could be also given by using singular integrals in the following way. So you have this definition of PV is the principal value of this integral that becomes singular and in the diagonal x equals psi. Okay. Moreover, it's inverse, that is to say, the Laplacian minus s is well defined and is given by the convolution of the His kernel. So it means that the kappa we have used before in the equation, kappa of f, is in fact the convolution of the His kernel with f. Okay. Well done. It's well known in the literature that the fractional Laplacian, this fractional Laplacian, I give to you now, has many equivalents, albeit from different definitions. So often, all the fractional Laplacians in Rn, they are equal, even if they have different definitions. Contrary to the Rn case, there exists different non-equivalent definition of fractional Laplacian operator in bounded domains. This is the main point I'd like to start to discuss, because somehow each problem you are in bounded domains you are resolving, you have to choose the best choice for your fractional Laplacian. This is the main point when you are talking about fractional Laplacian for scalar equations. The another point is when you are working with systems we are going to see soon, and you have to consider the exponents. But let's see what I'm going to talk about. So now we start also our work. We are going to talk the first scalar fractional equation in bounded domains. So we start with this paper. In fact, this is already published in 2018. It's a paper joint with Gerardo Aroto, which was our former student, and this was effectively his thesis. Okay. So we have considered the same equation like Caffarelli-Vasquez, but now in bounded domains. So omega is a subset of Rn, open bounded domain, having smooth regularity. The boundary has actually C2. You could think that the boundary is C2 regularity. Okay? So we have to decide, so U0 is the initial data, is just a measurable boundary function. We are going to assume that U0 is positive because we are going to think that U is some density, concentration, or absolute temperature, so it should be non-negative. Okay, so the initial data will be non-negative, and you look for U of Tx. But okay, so now this kappa will be defined from the inverse of the fractional Laplacian defined in bounded domains. And why you decide to work with the Dirichlet spectral fractional Laplacian instead of the restricted fractional Laplacian? Restricted fractional Laplacian, you think that you're outside the domain, the function should be 0. Because when you work with the Dirichlet spectral fractional Laplacian, we are allowed to give precisely the boundary condition in the boundary of your domain omega, I say gamma, okay? So since you are working with the Dirichlet data, U equals 0 gamma t, we consider the Dirichlet spectral fractional Laplacian. So it means that we already know that there is a spectral theory for the fractional Laplacian. Now you put a D here because of you have a Dirichlet condition, and from the well-known idea of spectral theory, you have a complete orthonormal basis. I'm going to say this just for the fractional spectral Dirichlet Laplacian, then I consider the same for the others, okay? And then you have the sequence of eigenvalues of your eigenvalue problem for the fractional Laplacian. So for your Laplacian, Dirichlet Laplacian. And then constantly you have the domain of your Laplacian, Dirichlet Laplacian is given by this expression. The Laplacian is defined this way. And you could apply the well-known stuff from Jacques Lillion's, the functional calculus, and you consider your spectral fractional Laplacian given this way. So this formula, it's well known. You have to prove some well important properties. It's more, I put here the name and the title of the paper because all of the details are written in this paper. You could go there and you will find all the details. So then we are working with the spectral fractional Laplacian with Dirichlet boundary condition. Okay? I see. So the next definition tells us in which sense use a solution of the initial boundary value problem. So we are going to say that a measure boundary function u in L2 of time, H1 means S, for any S from 0 to 1, is scalar weak solution when U satisfies, first, the heat type equation. So it means that since your equation is given divergence form, you multiply by a text function which does not see the boundary and integrate by parts. So you have your equation in the weak form. Now the initial condition is assuming strong sense. So you're going to say, remember that U does not have enough regularity to think that U restrict to 0 makes sense. Okay? U is just in L2 of time. So you are going to say that the essential limit of when time goes to 0 plus from this integral in L1 of U is equal the integral of U, L1 of U0. And more than that, we do not have enough regularity to think about the notion of the trace of U at the boundary. So we are going to give the notion of the trace of the boundary in the weak sense. This idea of the trace is exactly the one introduced by Felix Otto in his thesis to work with scalar conservation laws in bounded domains. So you are considered that the essential limit with some type of the deformation of your boundary, this limit exists and should be 0, which means that in some sense that U is 0. If U has enough regularity, it means that U is 0 at the boundary, gamma T. But this not, no, it's has said before, né? It's not clear that this integral exists as well because of the regularity, but since U is a solution, U be a solution of your equation, in fact, this integral exists. Now, more than that, next, we consider a more convenient way to express the concept of weak solutions given by the above ideas, these equations. So you have an equivalence theorem that says that a function U is a weak solution of the initial boundary value problem if only if they should satisfy this equation for each text function phi, where a text function now see the boundary in the initial data. And time t goes 0. Okay, so if you could show that your equation satisfies this equality, your solution, your function U is a weak solution of your problem. Okay, and then in that paper we could show this, and for that, I mean the more sophisticated ideas is to give the notion of the trace at the boundary. And then somehow you are going to perturb your equation point to like a Arrhenius viscosity method. And to get the compactness, we are going to use the idea of Aubin-Lyon's theorem, exactly in the paper from Caffarelli Vasquez, but now with some tricks because, in fact, this operator kappa does not commute with the gradient, which is in fact so used. Is so easy in the Rn case, which is not clear in this. It's not true in the bounded domains. Okay, so this is the first equation, and then we pass through the second equation, which is the second equation, the second scalar fractional equation in bounded domains. So somehow we are not so happy with this kind of Dirichlet boundary condition. It could be a normal boundary condition. Somehow you'd like to understand better the problem. So then you think this second scalar fractional equation in bounded domains. So this is the second paper with also Gerardo Warotto. And the title of the paper is Initial Mixed Boundary Value Problem for Anisotropic Fractional Degenerate Parabolic Equations. Okay? So all the details are in the paper, is already published online. You could see the details there. So now we are concerned with initial mixed boundary value problem. It means that the gamma, so I'm not going to put that omega is now, again, a bounded domain with C2 boundary, blah, blah, blah. Né? Então, gamma, which is a C2 regularity boundary of omega, né? Now is divided in two parts, gamma 0 and gamma 1, okay? And then we consider the following in Excel mixed boundary value problem. So dt of u, apply the divergence of q equals 0, u equal 0, the initial data, homogeneous boundary condition gamma 0, and normal boundary condition, the flux dot the null is the unit normal vector at the boundary, is 0 on gamma 1. So I have now Dirichlet homogeneous boundary condition on gamma 0 and normal boundary condition, homogeneous normal boundary condition gamma 1. Where Q now is more general than the other equation. Is degenerates again, could be degenerated. So this equation degenerates. You see that U is 0. Where U is 0, this equation degenerates. So you do not have more diffusive part. So is U dot the A of capital A of X, the against cap S of U. So this Q is said the diffusive fractional flux. We are thinking most of the time that Q is somehow, if we could fix that's the Fourier law, the general Fourier law. I mean, the general fractional Fourier law. So somehow you have here a gradient with the diffusive term A of X, AX of U, and here you should have gradient of U, but now you have a gradient kappa S of U, which means that you have a fractional Fourier law. You have said this in our papers instead of the idea of Fourier devices, which is a fractional Porous media equation. Okay? This kappa S is the inverse of the X fractional elliptic operator, LS of B. You are going to see so soon, where this matrix X is assumed symmetric and it should be continuous up to the boundary omega, and this ellipse sheets locally in omega. So this is the nice, I mean, it is in fact the minimal regularity we are interested to have the weak limits of the boundary condition gamma 1. So this is the sharp regularity. In fact, you are since your boundary gamma will be split in two parts, gamma 0, gamma 1, this is in fact the sharp regularity you should consider for the coefficients of the matrix H. And also, as usual, they should have some elliptic condition, so the matrix satisfies this for some constant capital lambda 1 bigger than 0. So this is now our more general problem, where Q is more general, and then you have split the gamma. Okay? So again, you have to decide which Laplacian we are going to consider in bounded domain. Well, since your domain is mixed, you have to consider a Dirichlet norm spectral fractional Laplacian. Well, again, a spectral fractional Laplacian, yes, because somehow you are interested to give the boundary conditions, in fact, in gamma. So you are allowed to do that. In fact, if you consider your fractional Laplacian, the restrict fractional Laplacian, for instance, you are not allowed to do that. Okay? So the elliptic operator L of U is minus the range of A, capital A gradient U, is the block building for the construction of the fractional Laplace fractional operator LS of B. Yeah? In fact, we were motivated by the paper of Caffarelli-Singer, really nice paper from Caffarelli-Singer. They are interested in another stuff, Harnack inequality and so on, fractional Harnack inequality and so on. And this paper from Henri Poincaré in 2016. But this idea of L of U, we came from them, okay? So L of B, will be the operator L subject to Dirichlet normal boundary condition. So this recursive capital B is in fact U equals 0. I mean, sorry, there is a type here, and this should be, oh, so yes, B of U go on 0, and we are going to consider that B of U goes 0. So I mean, exactly like this. So B if it goes 0, B is defining like this. So with this definition, we have a sequence of eigenvalues. With this sequence of eigenvalues, you could define your domain of this operator. E operator is given by this expression. And again, applying the functional calculus, we define for each s positive x the following fractional elliptic operator LSB given by this way. Okay? So this is the domain of the operator, and in fact, you define the same way the operator kappa s, which is the inverse of the LS of B. Okay? So which will be the solution of your solution? Again, your solution is given in your equation is given in divergence form. Then you think in the same way, you are going to integrate, you multiply a text function, integrate by parts. So definition of solution, what do we mean by a solution of our problem? So give initial data U0 in L infinity, so measure bounded function, for any s from 0 to 1, a function is L2 in time in the domain of this operator. In fact, in our paper, you have some relation of this domain of the operation LB with these exponents, with some from s from 0 to 1/2 to 1. This some equivalence, but I did not put here to show you more things. Okay, and this function is already bounded, so you also in infinity. So you have somehow you have a maximum principle for your problem. So we are going to say that the function with this regularity is a weak solution of the initial mixed bounded value problem when you satisfies. So now you give direct what the equality you consider. So the function should satisfy this equation. Now with a text function that's already, since the domain is split in gamma 0 and gamma 1, you have used the usual strategy, which is that take off the condition from your text function. So your text function is see the time t equals 0, but allows you do not see the part gamma 0 of the boundary, and then you are going to see what happens when you try to restrict your function to gamma 0 with this type of solution. So a function with this regularity will be a solution which satisfies this equation. Okay. Okay. You should think, well, this is a nice interpretation of the boundary mixed boundary data interpretation in this paper. In fact, the referee asked us to give interpretation of this initial mixed boundary data, and it become a real nice part of the paper. Okay, so let you be a solution of our problem 7 in the sense given above. No? We discuss first the Dirichlet condition. We have 3 cases. If S is from 0 to 1/2, so that domain for the solution, you are going to give you exact that U belongs to L2 from 0 to T in H1 minus S gamma 0 from S from 0 to 1/2. It means that here you have an exponent that is bigger than 1/2. So it means that you have the notion of trace. So in particular, this space naturally compares the Dirichlet boundary condition U equals 0 in the sense of trace. Okay, so if you are in this partial in this range from S, U0 is attained in the sense of trace. Okay. Okay. Now, if S from 1/2 and 1, it means that your function, your solution U belongs to L2 0T on H1 minus S. S bigger than 1/2, it means that H is less than 1/2. So here, the trace of U on gamma, it's not well defined. But we could give an interesting characterization, even this condition. What is this interesting characterization? Somehow, which looks like the 1/200 introduced by Jacques Lillons. So we are going to say that our space H1 minus S gamma 0, 1 minus 2S from S 1 to 1/2, if F belongs to 1 minus S, in the mean value for tau sufficiently small, nah? These expressions is of the order of tau 1 minus 2S. If S is bigger, let's say that S equals 1. So it means that O of 1 of 2. So it means that if S equals 1, if a function is just nearly 2, there is no sense of trace. So it means that this explodes with the order 1 over 2, which makes sense, as you know that if you do not have enough regularity in HS for S sufficiently large, you do not have trace. Okay? But there is a nice, more special case, which is that S go one half, which is more delicate because we do not have any precise identification of the domain of LB 1/4. Although, for the strategy of item 2 above, we have the following characterization. This is exactly the characterization of the referee asks us to give, and we succeed to do that. So you have now H1/2 gamma 00. Remember, most of you have already remember that the space H1/2 of omega, which is U in H1/2, that the integral of omega of the square of U divided by the distance of X to the boundary is finite. It's exactly the same here. But now no more the gamma, but now all the domain, but just gamma 0. So we introduce this notation to recall the H1/2 from Jacques Lillion. So we introduce this space H1/2 gamma 00, which are function from H1/2, which is this mean value. So if you pass to the limit using Lebesgue-Bezikovich differentiation theorem, we are going to end up with a tau which f of r it's in the boundary. So it says that the integral of gamma 0 and f r 0 is finite. So it means that you have a notion of the trace for function f in H1/2 that satisfies this condition. Okay, so this is the characterization of the Dirichlet condition, but the Neumann condition gamma 1. But the definition of X solution is sufficiently robust to give a sense of the Neumann boundary condition on gamma 1. More precisely, we state this boundary condition in a weak sense, rating as limits in the integrals of 0t times gamma 1. So somehow this is closely related to the other paper. So the essential limit as tau goes to 0 of this expression over gamma 1, over gamma 1 is 0. So this is the sense of the solution. Okay? So the main theorem says that there exists a solution for any s from 0 to 1. So now we pass from the scalar equations, so just one equation for systems of equation. Okay? What is the main point for the system of equation? So we start with a system which is in Rn. In fact, here are in R. Okay, so forget about bounded domains. So I don't care no more here for this system to consider which type of Laplace or fractional Laplace I have to consider, exactly given by the Fourier transform. But now there is another very interesting point related to systems, which is what type, which are the exponents I should use in each kind of equations in our system. Okay, so let us start with this on fractional Bénet type systems. Fractional Bénet type systems are well known to discuss about the short wave and long waves. It's very interesting. It was introduced by Bénet. In fact, the short wave is given by a Schrödinger equation, which this Schrödinger equation does not appear from quantum mechanics. This Schrödinger equation appears from some expansions in fluid mechanics. Okay, so the usual, talk about the usual Bénet system. It's a Schrödinger equation. So now instead of usual standard Schrödinger equation, you have a fractional Schrödinger equation. Okay, so we have, instead of the Laplacian, we have the fractional Laplacian. Okay, so this system is coupled. So now you have here fractional Schrödinger equation, and also now we consider fractional Bennet type system is given by a fractional Schrodinger equation coupled with a fractional porous media equation. So this is the fractional porous media equation, okay, which is coupled by this term with the first equation, and this is the equation that is coupled with the second equation. So now we replace the Laplacian by fractional Laplacian on S from 0 to 1, and here instead of this system is in just in R, and here used to have the gradient. In fact, the derivative with respect to x, because the usual Bennet system is just makes sense in R. So there is no Bennet system in Rn, but in fact, this system we are proposed here, you have replaced the gradient by the fractional Laplacian, with the exponent x divided by 2. So one could say, oh, I see. Now I see. If you send S to 1, you end up here with the usual Laplacian. You are going to end up here with the fractional Laplacian 1/2. But there is an equivalent relation with the fractional Laplacian with the gradient in L2. So it's because you do that, S and S over 2. This is not true. There are other ways to arrive at this simple naive equation, but I should say that the exponents in your system are mostly given, the good relation are mostly given by a priori estimates. When you start to work with a priori estimates, because how you resolve this system, you show local existence, and then you try to prolongate this system for each time. So to do that, you are going to obtain a priori estimates. And then when you're doing these a priori estimates, you could see that which is the best exponents to it. Okay. So what is the main one? The other two problems, the compactness were obtained by Aubin-Lyon's theorem, but here is not the case. The compactness in these systems is very, very complicated. Why? Because G is not strict monotone. So alpha, B, and gamma are real constants. The complex value function U is unknown for the fractional Schrodinger equation describe the short wave, and the real value function V is unknown of the fractional porous media equation describe the long wave. More than that, the function G is C1 regularity, could be Lipschitz, is assumed to be non-decreasing. Hence, degenerate zones for the state variable V are alloyed. So it means that in fact we are in a fractional porous media equation, because G prime could be 0. So it means that there are degenerate zones. And in these parts of you degenerate, it's very difficult to show compactness. Okay. So how we are going to show that? I mean, the notion of the solution of this system. What we are going to see, since this equation degenerates, we just expect that V is just nearly 2. So we have to consider exactly the notion of weak solutions. So give initial data, U0 in HS, V0 just in L2 and bounded. For any time t, a pair UV, which is in L infinity in time, enough regularity to the initial data. HS in R, L infinity in time, L2 in R, L infinity in R, is called a weak solution of the Cauchy problem 14 when it satisfies. Well, you multiply the first equation by phi, complex value function, tax function, complex value tax function, integrate by parts. No, not integrate by parts, but you use the idea that this Laplacian, you could pass the half of the Laplacian to the other side, okay? And for your porous media equation, do the same. Instead of you put some, it's not allowed to put any derivative in respect to G of V, because V is just nearly 2. So you pass all the derivative to the tax function psi, and here is the same. You pass all the derivatives. So a function U that satisfies these inequalities, you'll be called a weak solution of your problem. Main theorem. So U0 this class as just from 1/2 to 1, because you'd like to work in HS like an algebra. So to do that, to be a logic, to do that, you have to know that U is bounded. S should be bigger than 1/2 in R at least. Yeah? Your function G has a G prime which is bounded from above and could be 0 from below. Then for any time t, any t, global solution time, there exists alpha naught and an E naught that depends on t, capital T, such that if the modulus of alpha is less than alpha naught, or the cinetic energy, the modulus of U0 in L2 is less than E0, there exists a weak solution of this problem, of the Cauchy problem 14. And more than that, you have a maximum principle. You have a maximum principle for for the function V, which is the solution of the porous media equation. Okay? Well, let's see. We call that the fractional equation appears in water wave models. In fact, the fractional Schrödinger equation was introduced in the theory related to fractional quantum mechanics, associated of Levy process, as I said that from the beginning. The fractional Laplace is related to the Levy process. Moreover, the fractional porous media equation has been widely studied in the last years. I mean, if you look for the papers from Luis Vasquez, there are a lot of stuff related to the fractional porous media equation. One thing, another very interesting. How could you resolve this problem? How could you resolve it? So we are going to perturb both of equations. We are going to perturb the equation, the Schrödinger equation with the Laplacian, and we are going to perturb the porous media equation, fractional porous media equation, again with a Laplacian. But we are going to perturb with a different velocity. So for each epsilon positive from 0 to 1, and 18b positive parameters that will be chosen a posteriori, you consider epsilon from power A that multiplies the Laplace of U, and you consider epsilon from power B that multiplies the Laplace of V. It looks naive, but from the beginning, you do not have considered this idea. You just put epsilon Laplace of U, epsilon Laplace of V. We made a lot of, in fact, our colleague, our student, our colleague, Dionísio Orlando, make a lot of counts to get the estimates, lose all of the heads, and then you do not succeed, and we have this nice trick, nice idea. Well, let's put different powers, different velocities that sends Laplacian of U and V to 0, and then we succeed. Okay? So we perturb, in fact, also G instead of G, we consider G epsilon. So you get out the non-degenerate condition. And then now to pass to the limits as epsilon goes to 0 here is no more the trick of Abelian's theorem. You have to work, in fact, with the idea of scalar conservation laws. You have to, in fact, to introduce an entropy equation for the equation for V, and then use this entropy equation, but in fact, this is not a scalar conservation law. We have to adapt the idea of the Luc-Tartar, the idea of Luc-Tartar, which was written to scalar conservation law, where we succeed to adapt the theory of Luc-Tartar for this porous medium degenerate equation, and then we get the compactness with respect to epsilon, and we are able to send epsilon to 0 and went up to the definition of the solution. Okay? Well, this work is submitted, and you could find it in the archive, as well this second system of fractional that we are going to discuss now. So fractional hyperbolic Carré-Siegel. Now, so Carré-Siegel it's a well-known system in biology, which is related for the density of cells and chemotactic concentration. So let's start more quickly. I think I have enough time. So more 4 or 5 minutes. I mean, okay? No, more to maybe not 90 minutes. No, I think so. But there is enough time. You could interrupt me anyway. So the second system of fractional equations are the solvability of the fractional hyperbolic Carré system in 2022. You could find this paper in an archive. It's already submitted. And this is also a joint work with Gerardo Guarotto. So now we introduce this system does not exist at that time. So introduce the fractional hyperbolic Carré-Siegel model for chemotax. So is this the derivative in time of u by divergence of g of u, gradient kappa s of c, fractional Laplacian, Neumann fractional Laplacian, the one minus sc plus c equals u is strict to time t equals 0 in the initial data, and you have here the Neumann boundary condition gamma. With kappa s is the same operator that appears in the first equation. U is the density of cells, as said before, and C is the chemotractant. Just pay attention that this kappa s is not the inverse of the Neumann boundary, the Neumann fractional Laplacian. Okay? And I'm going to tell you why this could not be the inverse of the fractional Laplacian. So the measure of boundary function U0, the initial condition, is assumed to be non-negative in less than 1. Could because we are going to allow you to that do not have blow up. Okay. Observe that this equation is a hyperbolic equation. There is no, usually there are some usual Carré-Siegel mode. There is a Laplacian here, but we are working in the hyperbolic case. Okay. So you consider that the initial data is from 0 to 1. The normal fractional flux in the equation of U vanishes on gamma. That is, you assume that the boundary is characteristic. Then it's not necessary to prescribe the boundary condition for U. There is no boundary condition for U, which is very good, né? Because this assumption prevents some specific difficulties related to the trace of U. You do not have to care about U because the boundary is characteristic. Okay? Here S from 0 to 1, this Laplacian n of S denotes the Neumann spectral fractional Laplacian operator. So as usual, we are going to consider the eigenvalue. So we also consider the non-local operator kappa S given by definition, which cannot be interpreted as the inverse of the Neumann fractional Laplacian n of S. Why? This operator is defined for the eigenvalues of the Laplacian with Neumann boundary condition, and it is well known that the first eigenvalue is 0 and the corresponding eigenfunction is constant. Hence, the Neumann spectral fractional Laplacian is not an injective operator in its domain. Actually, it becomes injective when we restrict to the set from F in the domain of the operator when the mean value of F is equal to 0. So you could talk about just the inverse of the fractional spectral Neumann spectral fractional Laplacian when the value has mean 0. So this operator does not exist in general, and thus we are not allowed to write this operator like the Laplacian composed with the Laplacian minus S. 1 minus S like this, unless C, so this operator does not exist unless C satisfies the mean zero boundary condition, the mean zero condition, sorry. Now, due to the first eigenfunction of this operator be constant, you have the integral of this term equals 0. So if you integrate the second equation in omega, you end up that for almost all t, the mean value of C should be equal to the mean value of U, which implies that C satisfies condition 21, which is integral of C should be 0, even if U satisfies the same condition. So in order to C has integral 0, you should be integral of U 0. But we consider convenient that the function G of U is U times 1 minus U, the clock function, which prevents blow up. Indeed, from a maximum principle, we are going to show that your function U is non-negative and is less than equal 1, almost everywhere. Consequently, we could not impose that the chemical transit concentration C satisfies condition 21, means 0. Otherwise, U goes 0 almost everywhere, which means that you do not have any problem. Your problem is already 0 everywhere. This implies an inherent fractional characterization of the problem studied here. Well, I should say that this fractional characteristic problem was also a proposed problem by Caffarelli Vasque in this well-known paper from 2011 in ARMA. Okay, so we have followed some ideas from this proposal from that paper, but in fact we are more close to the paper from Pertami Dalibard. Let's see. The mathematical analysis combined the mathematical analysis to resolve this problem, combining two different aspects. First of one, the fractional calculus and the cinetic formulation of scalar conservation law. Remember that your first equation is scalar conservation law. Then to gain compactness, you are going to perturb like a Venice viscosity method. And to gain compactness, we are going to use the idea of rigidity result from Pertami Dalibard, and you succeed to adapt this to this fractional problem, this idea of the rigidity result from Pertami Dalibard in our case. We apply the cinetic formulation associated to the propagation of oscillation of the transport equation. What is this rigidity result of Pertami Dalibard? So you start with a scalar conservation law with the idea of cinetic formulation introduced by Pertami, Lyons, in Tadmor. And if your initial data does not oscillate, so if your initial data is 0, so your transport equation, which is transport, does not transport the oscillation. So it means that you gain compactness. This is the main idea of the rigidity theorem. So to this end, it is essential to use the renormalization procedure in the cinetic equation. I should mention that the property of uniqueness is not addressed, even the standard case from S go 1 from Pertami Dalibard, neither the asymptotic behavior. In fact, there is the main different point from the original system, because Pertami Dalibard succeed to show asymptotic behavior, but you could not do that use the ideas because you are completing different stuff because of the fractional problem. Well, since the first equation in our system, characteristic system, is a hyperbolic scalar conservation law, you have to consider the notion of entropy solutions. So we introduce the idea of entropy for your first equation. So as usual, we are going to say that Et is a Lipschitz continuous function, is a convex if satisfies this condition, blah, blah, blah. This is well stuff from the scalar conservation law. Okay? Since we are going to work with the idea of cinetic formulation, it's well known that you should consider, it's nice to consider the Kruskov entropies, or more convenient to use the semi-Kruskov entropies, which are related to sino plus and sino minus. Okay? So instead of modulus, you consider modulus plus and modulus minus, and instead of your flux function, Kruskov flux function, original one, you are going to consider plus and minus. It's very important in order to gain the idea of the rigidity theorem. So what we are going to say that our definition of solution. So given initial data, which is in infinite, satisfying to ends, and NS from 0 to 1, definition. A pair of functions U, C in infinite, and U in just in infinite, from 0 to infinity to omega, times infinity in time in the domain of this operator, you'll be called the weak solution of the fractional hyperbolic characteristic system if for almost all t, the pair of functions UC satisfies the first one, it's inequality, as usual from entropy solution for scalar conservation laws. Okay, so we multiply by an entropy and use the idea of scalar conservation laws, and then you get the entropy equation, and then you integrate by parts and get this function, where phi is a text function which sees the boundary, okay? And we have also the equation for your C, which is elliptic equation, and then as usual in idea of Stokes' equation for fluid mechanics, you get this equality for each testing function C in H1 of omega, okay? And then, I mean, as usual, how are we going to resolve this? How are we going to resolve this? Sorry, the theorem. Let the statement of the theorem. So give initial data in infinite. Now from S from 0 to 1.5, then there exists a pair of functions in this class, which satisfies which weak solution of our problem, and more than that, you have a maximum principle for U and C for each time t positive. Well, the definition you have considered for any S from 0 to 1, but in a statement of your theorem, you have just considered from 0 to 1.5. But most of the time I see from 1.5 to 1, Vladimir. Yes, remember that in our problem, you have the Laplacian for, sorry to come back to the equation. Remember that in our problem, instead of Laplacian S, you have 1 minus S. And this irregularity for C, will be very important when you're trying to use the renormalization procedure for transport equations. So we are going to work in the idea of Ambrosio, with Ambrosio, or even it's a way to use the Lyon's the Lyon's stuff to transport equations, and then to get the renormalization procedure to end up with if you need. It's just a lot. You have to restrict ourselves for the exponents S from 0 to 1.5. Okay, I mean, when you are going to show the renormalization, when you are going to use the renormalization procedure to get the rigid theorem, to rigid idea of the theorem, to show compactness, and apply the Lyon's theorem, the renormalization, you should have to consider these regularities. I mean, finally, I should comment more two nice problems which we are going, which are in progress, in preparation, but they are in progress. But I should say that's almost finished, both of them. The first one is again a scalar equation, but now is no more a Ritz type equation. It's a Dirichlet problem for degenerate fractional parabolic hyperbolic equation. So it's a scalar conservation law with a parabolic degenerate term, and this term degenerates. This term degenerates. So it's very different when you're going to consider non-homogeneous boundary condition, and then you are going to get the compactness result. Is not trivial stuff, but he succeed to do that. And also, I should say another work which is related to systems. Now with Lauren Bonaldo, which is nowadays our postdoc here at UFRJ, Universidade Federal do Rio de Janeiro, and which is related to the fractional Laplacians, but now with the elliptic system. Okay, So thank you. Thanks for your attention, and welcome to discuss anytime. Thank you all.
Thank you, thank you, Wladimir. Congratulations for excellent talk. And now it's open for question for Wladimir.
Yeah.
Wladimir, I have a simple question and more curiosity about the linear problem. You have S near 1, the hyperbolic problem. The behavior, the S converge to 0. You have the parabolic problem. What happens when the S decreases 1 for 0?
Yes, somehow the fractional Laplacian S, when S goes to 0 plus, I mean, the operator becomes the identity, okay? And S goes to 1, it becomes the usual fractional Laplacian, which is the local behavior, okay? So in that first paper that we did with Gerardo Garoto, we give the nice ideas which type of equations we went up when you send S to 0 and you send S to 1. So it's very interesting. You could pick up this paper from mathematical method models, M3S, in the applications, and then in that introduction, we make some assumptions to say not assumption, just to make a discussion, a formal discussion, which type of equation you could get when you send S to 0 to 1. So more or less, when you send S to 0, we end up exactly with a scalar conservation law, with type of conservation law, and we send S to 1, you get the usual Laplace equation. I mean, it's not the heat equation. Remember that you did T of U plus divergence or equals divergence of U grade kappa of U. Okay, so this is a nonlinear term. So this kappa goes to identity as 0 goes to 1, and then you end up with a like a porous media equation. But you could see there, in the first paper I showed in this talk, so the paper from 2018.
Thank you, Wladimir.
Okay.
More question? Olha aí, look for the chat.
The chat. Let me put it in. Where is the chat? I mean, let's.
Camila Soares.
I could not see the chat. Okay.
Curiosity.
When do you characterize H? Do you consider it to be the only way, or did you share it because it is the most intuitive? Which H is you're talking about, Camila? Which capital H? Which capital H? I mean, well, the X space is arising with the idea of the estimates, the a priori estimates, But I mean, usually you do the stuff like usually in partial differential equations. Yes. You think that your solution with enough regularity to get that we end up with the minimal regularity space that you could work with. Okay. More than that, dear Wladimir, thank you for the very nice presentation. Oh, Primeco, nice to hear for you, Primeco. Thank you so much. Thank you.
It was very nice to see you. Graças à tua internet.
Ok, Slava. Thank you. Obrigado, Slava. Muito obrigado.
Can I speak português ou...
Yes. Claro. Por favor.
Wladimir, tá? Agradeço pela interessante apresentação, como os resultados eu gastei muito. Eu tenho uma pergunta seguinte. Você tem alguns resultados trabalhando com as equações diferenciais parciais, tá? Fracionárias, onde a fracionária é introduzida através de derivadas com respeito do tempo?
Perfeito.
Você tem alguns resultados?
Não. Isso, mas eu quero dizer, tem um trabalho do próprio Caffarelli com Vasquez e, na verdade, acho que também com Vasser, que eles utilizaram a derivada de Caputo no tempo, né? Que é uma dimensão, é mais fácil ter a caracterização da derivada.
É verdade.
Eles usam exatamente a derivada de Caputo no tempo. Tem algumas relações com essa que a gente está utilizando, né? Tem um survey do Miroslav Stilihavi, exatamente relacionando todas essas ideias, o divergente fracionário, o gradiente fracionário e o próprio Laplaciano fracionário, inclusive com essas derivadas do tipo Caputo, que são dadas por transformada de Fourier, quer dizer, no domínio todo, né? Então, posso te passar depois, Lava, mas não, eu, em particular, não tenho nada com derivada fracionária no tempo, que também é muito interessante. Tem bastante.
A gente pode combinar, eu poderia te enviar o meu resultado obtido mais ou menos 6, 7 anos atrás, junto com um professor italiano, Alfredo Lorenzi, tá? Ligado com o sistema do BO-JKD, tá? Onde exatamente um sistema como um termo que caracteriza a derivada fracional com respeito do tempo, tá? Lá, infelizmente, o máximo que a gente conseguiu provar o teorema da unicidade e um tipo de como dizer isso? Dependência contínua, tá? Tá? Dos parâmetros do problema.
Dependência contínua dos parâmetros.
Isso. Mas eu tenho na cabeça alguma coisa para fazer além disso, tá? E gostaria muito de discutir com você, tá?
Podemos... Prazer sempre. Ok, João. Pode ser, com certeza.
Tá. Então, eu vou entrar em contato com você e a gente vai discutir, tá?
Tá bom. Obrigado.
Okay.
Obrigado a você.
Obrigado, Pimenta. More question? Bom, então vou aproveitar e falar em português. Agradeço aqui o Wladimir, uma honra ter o Wladimir aqui, diretor do Instituto de Matemática, professor titular da UFRJ. É um prazer tê-lo aqui no nosso seminário. Você é sempre bem-vindo, tá? Então, vou passar agora para a palavra do Juan para fechar aqui o seminário do dia. Obrigado, Wladimir. Obrigado a todos.
Thank you, Mauro, and thank you a lot, Professor Wladimir Neves, for your amazing talk.